Welcome. This video is going to take a look at something known as the method of initial rates. It's a common experimental method used to determine the reaction rate order. So you determine the reaction rate order by actually comparing the initial rate of a reaction carried out with different concentrations of the reactants. So sometimes in a problem, they'll simply tell you the reaction rate order is to the second order for reactant A, and it's to the third order for reactant B. But other times, you have to actually do the experiment, evaluate the data, and determine the rate order. So that's what this video is going to attempt to show you. The initial rate looks at how fast the reaction proceeds at the moment the reactants are mixed. So if you double the reactant, what happens to the rate? Well, the rate could remain unchanged, or it could double, or it could quadruple, or it could increase 8 times. Those are the most common possibilities. But the rate could change, or it could remain unchanged. So if you double the reactant and the rate remains unchanged, what does that tell you? That means the reactant is considered to have no effect on the reaction rate. It means the other reactants apparently affect it, but not this particular reactant, so we say it's the zero order. If the rate doubles when the reactant concentration of the reactant is double, then it's said to be first order because the effect on the concentration had the same effect on the rate, which is 1 to 1. If the rate quadruples, the reactant is said to be second order because doubling the rate quadrupled or increased the rate 4 times. So you can think of it as 2 to the second power. If the rate is 8 times greater, the reactant is said to be third order because doubling the reactant's concentration caused a 2 to the third or an 8-fold increase. So, and you could go on and figure out what it would be for fourth and fifth order, but 0, 1, 2, and third order are really the most common. So another way to simplify this is that the order or exponent in the rate law means if you double the concentration of the reactant and there's no change in the rate, it's zero order because 2 to the 0 order would be the same as multiplying by 1. If you double the rate when you double the concentration, then it's first order because 2 to the first would mean it's simply double. If the rate quadruples, it's second order because 2 squared is 4. If it increases 8-fold, it's third order because 2 to the third is times 8. So let's look at this data for a basic experiment where you have reactant A plus reactant B yielding some product. And we have 3 different trials of data to compare, and for each trial we have the initial concentration of both A and B as well as the initial rate of the reactant. So what differs between the 3 trials? Well, from trial 1 to trial 2, we notice that B remains unchanged, but reactant A is doubled. So our question is, if A is doubled, if I have 2 times the concentration of A, what happened to my rate? Well, I could see that my rate also doubled. So if doubling A doubles the rate, that's said to be first order. The effect on A is the same as the effect on the rate. It's a linear or one-to-one relationship. So I'm first order for reactant A. Between trial 2 and 3, now A remains the same concentration of A, but the concentration of B doubles. And now when I look at the effect on the rate has quadrupled. So now this is said to be second order in B. So my overall rate is considered to be third order, and if I wrote an equation for the rate, it would be rate equals K times the concentration of A to the first power times the concentration of B to the second power. And as I said, that would be a third order reaction rate overall. So here's some similar data. I want you to evaluate it and see if you could come up with the rate order for each reactant and write the overall rate equation. So if I look at the trials, and again, I want to see what varies from trial 1 to trial 2 to trial 3. So between trial 1 and trial 2, I see that my concentration of B remains unchanged, but my concentration of A doubled. And so if I look at the effect on the rate, I see there's no effect. So that means it's zero order in terms of reactant A. Change in the concentration of reactant A has no effect on the reaction rate. If I look at trial 3, the difference in trial 3 is that from trial 2 to 3, concentration of A has remained unchanged, but the concentration of B has doubled. And now if I look at the change in rate, the rate has also doubled. That means B is first order because there's a one-to-one relationship. Doubling concentration doubled the rate. So my rate would be K, my specific rate constant, times the concentration of A to the 0 power times the concentration of B to the first power, which would be considered a first order overall, or this could be simplified to just K times the concentration of B. In this one, I've given you information, and I want you to determine what the initial rate should be for trial 3 based on the information you've been given. So again, I encourage you to pause and try this on your own. When I look at this data, I look at trial 1 and 2 and see that A has been doubled. Now there may be other reactants that affect this, but we're only concerned about A in this case and the change in A, so we can assume all other things are being held constant, the other reactants if there are any, the temperature, etc. So when I look at doubling A from 0.1 to 0.2, I see that my constant went up a bit. So how much greater is that? Well, if I take 10.8 times 10 to the minus 11th and divide by 2.7, I see that that is 4 times as much. So doubling A caused the rate to quadruple or increase 4 times. So that lets me know A is in the second order. So between 2 and 3, I've doubled my concentration again, so I could expect that this should quadruple again. So if I go ahead and take that times 4, I expect a 4-fold increase, I would come up with 43.2 times 10 to the minus 11th as the predicted rate when my concentration goes up to 0.4.